In this video, we're going to be talking about graphing nonlinear functions. And we're going to start off with this guy. F of x equals negative x minus 4 quantity squared plus 2. So one of the first things that you need to do anytime you need to graph a nonlinear function is that you need to identify what kind of shape you're going to be working with. Now, in this problem, we see that we have a square. And the square tells us that our shape is going to be a parabola. Okay, so it's going to be that U shape, the guy that we've seen many, many times. And now we just need to figure out what have we done to this shape. How have we shifted it up, down, left, and right? Is there a stretch or a compression? Is there a reflection? And that's what the rest of the information in the function tells us. So if we look, we see that there's a minus 4. And when there's something being done inside the main part of the function, in this case inside of the square, that tells us a horizontal shift, and it's going to be the opposite of what we see. Remember the little acronym that we've talked about? We have talked about IHOD over. So anything that is inside the function is a horizontal shift, and we do the opposite of what we see, and that will affect our domain, or it can. So I see the minus 4, which means instead of going to the left 4, that means I'm actually going to go to the right 4 units. And then I have this plus 2 that is on the outside, this plus 2 that is not being affected by the square. So since this is outside the main function, it's a vertical shift. We do exactly what we see, and it has the potential to affect our range. So I see this is on the outside. It's a vertical shift. I'm going to do exactly what I see, so plus 2 means to go up 2 units. There's one more thing to note here, and that is it's that leading negative right there. So if you have a negative in front of your function, in front of the main part of your function, this means that we're going to have a reflection. We're going to reflect across the x-axis. Basically, we're going to take this parabolic shape and we're going to turn it upside down. So we're going to have an upside down parabola that is going to be shifted to the right 4 and then up 2. And so that's how we graph these guys. We don't need to create a new t-table of values. We just take the key points that we have from our parent functions and we just move them to a new location. Now when we do this, I oftentimes want to go ahead and mark that vertex, mark that main point, and then we're going to build from there. So we're going to go to the right 4 and go up 2. So let me go ahead and mark this. And I'm just going to dash basically a new set of x and y axes where that key point is going to act as our new origin. Okay, so we need to graph a parabola that's now upside down. Now I don't need to worry about the right 4 and the up 2 because I already have that here with my new vertex. So if we think about what this is supposed to look like and those key points from before, we just kind of count off and we mark off on our new x-axis. So 0 squared is 0, right? 1 squared is 1, but it's a negative, so that means go down 1. And you may be asking, why am I squaring? Well, this is where we now go back to the main part of our function. The big idea for this function is that it's a squaring function. So every unit that you go up, we're going to be squaring that value. So 2 squared is 4, and when you count this, count from the new x-axis. So that's going to be 1, 2, 3, 4. 3 squared is 9, so that's 4, 5, 6, 7, 8. And we're going to be down 9. And we know with parabolas that there is this vertical line of symmetry. So I can copy these points onto the other side. So there's down 1, down 4, and down 9. And since this is a parabola, we draw a nice parabolic shape that is upside down because of the negative, and it has been shifted to the right 4 and up 2. So sometimes parabolas can be kind of hard to draw. Just understand that they never curve back onto themselves. They are never vertical on the ends. They keep opening and getting wider and wider as we go out. All right, let's try something else. Let's take a look at this function. G of x is equal to 3 halves times the absolute value of x plus 1 minus 4. One of the first things that you should notice in this function is the absolute value. So having absolute value means that we're going to have a v-shape. All right? We know it's a v-shape. We just have to figure out, well, where's everything else? Okay? So we look inside. Inside we see +1. And as we mentioned earlier in this video, if it's inside, it's a horizontal shift, but you're going to do the opposite of what you see. I see a +1, so that means I'm actually going to go to the left 1, so in the negative direction. And then I see a -4 on the outside, so the -4 is outside. It's a vertical shift, and we do exactly what we see. So -4 means that we're going to go down 4 units. And what about that 3/2? Well, this 3/2 is a coefficient in front of that main part of the function, in front of that parent function, which is the absolute value. If it's greater than 1, it's going to take our v-shape and it's going to stretch it. If, however, that value in front is less than 1, it's going to be a compression and it's going to try to flatten that normal looking v-shape. Well, 3/2 is a value that's greater than 1, so that means that we do have a stretch. So we have a stretch by a factor of 3/2. Now here's something to understand about absolute value functions. These are really some of the easiest guys that we can graph because I can use this value right here just as a slope. You can look at that just like rise over run. Now you can't do this for the other functions, but you can do this for absolute value because they are made up of straight pieces. They have linear sections to them. And so if they're linear, it's really easy to go up 3/2, just like you would for the slope. But before I do that, let's go ahead and plot that new vertex, or that new origin. So we have to go to the left 1 and down 4. So left 1, down 4, there is my new vertex. And you're going to see me do this every time I graph. I'm going to draw a new set of x and y axes where that guy is my origin. Now, I could label this and say, okay, this is going to be my new 0, 1, 2, 3, and so on. But I mentioned with absolute value and their linear sections that I can just take this 3/2 and use it like a slope. So from here, I'm going to go up 1, 2, 3, and over 2. And I'm going to keep doing that until I run out of space. 1, 2, 3, over 2, up 3, over 2, and so on. And you want to do that on the other side, on the left side, to get more points. 1, 2, 3, over 2, up 3, over 2, and so on. Now if we've done this right, we can take our straight edge and things are going to line up very nicely. So we have that half right there, and then we have this other guy right there. Remember that when you graph, you need to graph to the edge of the graphing window, put arrows on the ends, and everything's going to be fine, right? So let's try some more and see what we can do here. So here we have h of x is equal to -2 times the cube root of x plus 6. So let's make sure we understand the shape. So we have a cube root, and the shape for the cube root is that funny looking worm. That's usually what we call a little worm guy. He's like the cubing function that looks kind of like an S shape or a cactus guy, but he's laying down. He fell over. So he looks like a sideways cactus. Something like that. So that's just a general idea about the shape. Now let's see what we've done to this. Inside the cubing, or inside the cube root, we just see x. There's no plus or minus in numbers, so there's no horizontal shift. But then outside, we see plus 6. So I do exactly what I see, and I'm going to go up 6 units. And then in front of the cube root, I see a -2. So we've got a couple of things going on here. So one of these is a reflection. So we're going to be reflecting across the x-axis. And that's because of the negative. And the 2 means that we're going to have a stretch. So stretch by a factor of 2. So all of these key points that we would have had for our original cube root are now going to be stretched and doubled, so it's going to stretch it out vertically. Okay? But before I do all that, let's make sure we get the key point down. So this guy normally goes through the origin. So we're going to take that key point and create a new origin. And there's no left-right movement, it's just up 6. So from here, go up 6, and that is my new key point, my new base point. So here's my new x-axis and my new y-axis. Now, in order for us to work with the cube root function, we need to remember those key points. Okay, so normally for f of x is equal to x to the third, here are the key points. You plug in -2, you plug in -8, you get -2, plug in -1, you get -1, 0 gives you 0, 1 gives you 1, jumping ahead I guess, and 8 gives you 2. So we're going to take these guys and now plot them relative to this, but there's going to be a bit of a change here. See, we've got this 2, right, really a -2 in front, so it's going to take these guys and turn them upside down and then stretch them by 2. So here's 0, I would next care about 1, and then I would care about 8. So your normal cube root would say that you would have a point here at 1 and then a point here at 2. Just kind of going along with what we see here. 1 gives you 1, 8 gives you 2. But now we're going to take this and turn it upside down and multiply it times -2. Or multiply it times 2. So instead of going up 1, you're going to be going down 2 units. Instead of going up 2, multiply that value by this -2, and that gives you -4. So down 1, 2, 3, 4. So instead of it curving up and out like that, it's now curving down, and it's got a stretch to it, so it's going to be a little bit steeper. On the other side, here's -1 and -8. The cube root of -1 would have been down here, right? But now multiplying times -2, so it flips upside down, and a multiply times 2, so it's going to be up 2 units. The cube root of -8 is -2. But times -2 makes it go up 1, 2, 3, 4. I know it's a little bit off the grid, but it kind of helps us know where we're supposed to be aiming once we do leave. One of the key things we need to understand about the cube root shape is that right here instantaneously it's going to be vertical. So we kind of exaggerate that a little bit before I curve out to the right. And do the same thing kind of vertical here until it curves out to the left. And so that's what this cube root function would look like. We moved it up 6 units, and we took this shape right here, we turned it upside down, so now it's kind of doing this, and then we stretched it. So that stretch of 2 makes it look like this.